So here we have the 2023 paper, question 5, involving differentiation. So we're just going to be going through it just step by step, just so any questions that arise, hopefully they're answered in this video. So question 1 of part A says the function f is defined as follows: for x being an element of R, f of x is equal to 1 over 5x squared plus 7. Find f prime of x, the derivative of f of x. Give your answer in its simplest form. So there's two ways to do this. First of all, we have one number over another, so we can go straight ahead and just do the quotient rule. Where the top one's going to be u and the bottom is going to be v. So if we do that one, we're going to have u being 1, so du is 0. And then if we have v is equal to 5x squared plus 7, the derivative of that is going to be 10x. So if we go through it, we're going to have 5x squared plus 7 multiplied by 0 minus 1 times 10x, and this whole thing gets divided by 5x squared plus 7 all to be squared. So if we look at that, this 0 cancels out the 5x squared, so all we're left with then is going to be negative 10x all over 5x squared plus 7 all to be squared. And this is using quotient rule, which is v du minus u dv all over v squared. The other way we can do it is using the chain rule, and that's by noticing that f of x can be rewritten. Anything that's 1 over and then the something on the bottom of it, we can rewrite that as the bottom number to the power of negative 1. So this is actually equal to 5x squared plus 7 all to the negative 1. So if we're finding f prime of x, then we're going to first of all have to differentiate this upper power. So we're just going to have to decrease that by 1 and multiply by the other power, same as always. So then we're going to have minus 1 multiplied by what the inner function is, 5x squared plus 7. Drop it by 1, we have the negative 2. And now with the chain rule, we also need to multiply the derivative of the inner function. So this all gets multiplied by the derivative of 5x squared plus 7, which is 10x. And if we multiply all that out, we're going to have minus 10x multiplied by 5x squared plus 7 to the negative 2. And then if we tidy that up, we just have negative 10x all over 5x squared plus 7 squared. So you can see these two are the exact same, just using two different methods. So if we go ahead and look at part B of this question, we have the function g of x is defined as follows: for x is an element of R, where x is some number strictly less than pi and strictly greater than 0, where g of x is equal to the tan of x over 2 multiplied by the natural log of x. Find the value of g prime of pi over 2. Give your answer in the form a plus the natural log of b, where a and b are real numbers. So if we're looking at this, we can see that this is multiplication of one function and another function. So first of all, if we're using the product rule, we're going to have to use the product rule, which is u dv plus v du, where the tan of x over 2 is u and the natural log of x is v. So u, we're going to have the tan of x over 2. And if we find du, it's going to be equal to a half x squared x over 2. Why is it equal to that? Well, tan of x over 2 is the same thing as the tan of a half of x. Because we have a half multiplying the x, or we have x divided by 2, we have x being acted on by something else, and then it gets plugged into tan. So we actually had to use the chain rule right here. So we multiplied by the derivative of what was in the inside. The derivative of a half x, well, the x just goes to 1, so that's equal to half, which is why we had to multiply it back in here. And then we have the derivative of tan is equal to sec squared. So if we continue doing this, we're going to have v is equal to the natural log of x, and the derivative of the log of x, or the natural log of x, is 1 over x. So now we can use the product rule. So u is tan of x over 2, and that gets multiplied by dv, which is 1 over x, and then we add v, which is the natural log of x, multiplied by du, which is half sec squared x over 2. Now, if we look at our rules and we go to the section all about trigonometric identities, what we have here is a half sec squared. And if we look at the very top, we have the sec of a is equal to 1 over the cos of a. So that's what we can use. So if we have sec of a is equal to 1 over cos of a, it means that sec squared of a is equal to 1 squared all over the cos squared of a. So right here, we have a half times sec squared, as we said, was going to be 1 over cos squared pi over 2. Sorry, x over 2. And it just makes it a little bit easier to deal with. So if we go ahead and find g prime pi over 2, that means that we now have the tan. And if we stick pi over 2 over here, we're going to have pi over 2 divided by 2, which is pi over 4, plus 1 over pi over 2. And then we have the natural log of pi over 2 multiplied by a half, which again is multiplied by 1 over cos squared pi over 2, divided by 2 again, so divided by 2 again means that we're going to have pi over 4. Remembering these, tan of pi over 4, we have the cos squared of pi over 4. What do we get? Well, if we go back to the tables again, we have tan down here, and if we look at where pi over 4 is, we can see that that one's equal to 1. And then if we go to 1 over cos squared, we're going to have cos of a. When we stick in pi over 4, we're going to get 1 over 2. So right here, this is equal to 1. This second one, we just flip the bottom fraction, so then we get 2 over pi. The natural log of pi over 2 stays the same, half stays the same, and this one goes to 1 squared all over 1 over root 2. Both of them are going to be squared, so that's going to be equal to 1 over 2, or 1 over a half, sorry, which is just equal to 2, because again, we flip this bottom one. So this whole thing is going to be equal to 2. So if we go ahead and simplify it, we're going to have 1. That shouldn't be a plus there, apologies. Multiplied. 1 multiplied by 2 over pi. And now we have to add on the natural log of pi over 2. And again, we're going to have to multiply this whole thing by a half and 2. So in the end, we're going to have 2 over pi plus the natural log of pi over 2. Because 2 multiplied by a half just gives you 1. So part C now. So the diagram below shows 3 sets, A, B and C, and 2 functions f and g, where f is a mapping from A to B, g is a mapping from B to C. The number of elements in A is the number of elements in C, which is 4, and the number of elements in B is equal to 3. Find the value of g of f of 3. So whenever you have anything written like this, we have g of f of 3. What we want to figure out first is what happens when you stick 3 into f. So say, for example, f of 3 was equal to 2. We'd have f of 3 equal to 2. So we now stick this into g. So then we'll be looking for g of 2, where this 2 comes from f of 3, and this whole thing just gets mapped all the way back. So if we look at this set, we're looking for f of 3 first of all. So set A, this one over here, what happens with the mapping f? So if we go from 3, it sends it to this picture of the earth. What happens when we stick this picture of the earth into the function g? It goes to w. So in the end, we have g of f of 3 is equal to w. So explain why g B to C is injective but not surjective. That is 1-to-1 but not onto. So we don't really need to worry about what's happening in A. So we look at B and C first of all. What we want to notice is that if we look at everything in here, the plane, the world, and the rain cloud, they all get mapped to one thing within G. So everything in B gets mapped to G. So that's okay. So that's why we can say that this is going to be injective. Now, why is it not surjective? Surjective occurs when everything in the subset gets mapped to by something in the primary set. So if we look at B again, B maps 3 things to X, W, and Z, but nothing gets mapped to Y. So if we were writing down anything, we know it's injective because B maps every element to C. And why it's not surjective, not every element in C gets mapped to from B. And there we have it. So we're going to be taking a look at the higher level Leaving Cert 2022 paper, question 10 on paper 1. So a student is asked to memorize a long list of digits and then write down the list sometime later. The proportion p of the digits recalled correctly after t hours can be modelled by the function pt is equal to 0.82 minus 0.12 times the natural log of t plus 1 for some value of t strictly greater than or equal to 0 or less than or equal to 12, where t is a real number. Find the proportion of digits recalled correctly after 3 hours according to the model. Give your answer correct to 2 decimal places. Gives us a time, t is a function of time, so then if we find p of 3, that's going to be equal to 0.82 minus 0.12 times the natural log of t, in this case 3, plus 1, so the natural log of 4. And if we were to compute that, we'd end up with the value 0.65, rounded to 2 decimal places. Part B. After how many hours would exactly 55% of the digits be recalled according to this model? Give your answer correct to 2 decimal places. So before we were plugging in a value of time, now we're looking for the time. So in here we have 0.55 is equal to 0.82, subtracting 0.12 times the natural log of t plus 1. So we're looking for t here. I want to first of all figure out this part in a positive sense. So I want to move that to the left hand side. I'm going to move the 0.55 to the right hand side. So I'm going to get 0.12 times the natural log of t plus 1 is equal to 0.82 minus 0.55 gives you 0.27. Now I'm going to divide both sides by 0.12. I have the natural log of t plus 1 is equal to 0.27 divided by 0.12. And if we were to calculate that, it would be 2.25. Now, how do I get this t outside of it? Well, if you remember your rules of logs, I can raise both of these. I can raise e to the power of both of these, which will bring the locked logarithm inside here all the way down. So when we raise e to the natural log of e, that cancels it out. So the answer for this one would give you t plus 1. Whereas on the other side, we just have e to the 2.25. And now I just need to subtract 1 from both sides. E to the 2.25, subtract 1. Oop. So I get t is equal to 8.49 hours. And again, just to clarify, this method here crops up the whole time when we're dealing with logs. Although we're not dealing with calculus just yet, like the rest of this video is, it's important to remember your logs and just know them for the Leaving Cert, because if you don't remember this, it could be a nightmare and you'd only get down to here, so you'd be getting half marks or even if that for this question. So you just be dropping marks where remembering this one fact or knowing where to find in your tables, which we go over the tables. We can find our section all about logarithms right here. And if we look at the right hand side here, we're gonna have 2 things. Well, we can look at the top one actually. If we take our number here and we find the base of a to the power of y, it gives us x. And also we have the second one where if we log to the base of something where where the base of that is going to be in here, we get the x value. Apologies for not really making that sense. And also the final one is probably the most important aspect of it. We have a to the log of a to the x is just equal to x. So what this does is if we take our value of a and raise it to the logarithm of that base, whatever the x value here is going to be brought out. So in our case, we had the natural log of t plus 1. The natural log is the same thing as log to the base e. So here actually we have a, which in this case I called e, raised it to the natural log of e to the t plus 1, where this thing was equal to x. So this whole thing was just equal to t plus 1. So let me explain that again. If we go over to our table section, if we look at page 21, on the top right hand corner, we're going to see this identity here, or this rule right here. So if we have some number a, and we put a to the power of the logarithm of a to some value x, that equals to x. So in the example we were just given, we were trying to figure out how to get this t plus 1 out of the natural logarithm. Well, what is ln of any number? Well, that's log to the base e. So by raising the natural log of t plus 1 on top of e, or raising e to the ln of t plus 1, it just meant that whatever was inside the brackets of the natural logarithm came out. So this was equal to t plus 1. And that's how I was able to take that out and just find t as itself. Now, find the value of p prime of 1. So first of all, we have to remember that p of t was equal to 0.82 minus 0.12 times the natural log of t plus 1. So now we just need to differentiate this, and then whatever the derivative of that is, we can sub in 1, and that's how we figure out this. So p prime of t, first of all, the 0.82 is a constant, so that disappears. Then we have minus 0.12 times the natural logarithm of t plus 1. The minus 0.12 stays there. And then at the bottom, we just have the natural log of t plus 1, which just goes to 1 over t plus 1. So that's how we figure that one out. Now what we want to do is we want to find the value where p prime, and we sub in 1. But that's going to be negative 0.12 all over 1 plus 1, which is negative 0.06. P prime of t is always negative for values between 0 and 12, where t is a real number. What does this tell you about the proportion of digits recalled correctly after t hours? Well, what is p of t, or p prime of t? It's going to be the rate of change of pt. In other words, it's going to be equal to the slope. What happens when the slope is always negative? Well, then we're going to have that the number, or the proportion of digits recalled correctly after t hours, is always going to be decreasing. I.e., the further we move along between 0 and 12, the less digits you're going to remember. So part D, use calculus to show that the graph y is equal to pt has no points of inflection. Points of inflection, as we'll cover a bit slightly more later on, we're going to have the derivative of the derivative. So p double prime of t, well, we had negative 0.12 all over t plus 1. If we use the quotient rule for this, u and v, we're going to have u being equal to minus 0.12, so du is equal to 0. And then we have v is equal to t plus 1, so then we have dv just equal to 1. Plug this back into the quotient rule. We're going to have v du, so t plus 1 times 0, minus 0.12 times 1. Double negative here, this left hand side goes to 0, so we just have 0.12, and then this is all going to be divided by v squared. So if we look at v, we have t plus 1 squared, so this is all going to be over t plus 1 squared. What does this mean? This means because for this to equal 0, we're going to have to multiply both sides by t plus 1 squared. So in other words, what we're actually going to have is 0.12 all over t plus 1 squared equal to 0. If I multiply both sides by t plus 1 squared, what I'm actually going to get is that 0.12 equals 0, which it doesn't. So because this doesn't make sense and we can't have 0.12 equaling 0, we can therefore say that y is equal to p of t has no point of inflection. Again, in the next question here, I'm going to be dealing with points of inflection, so I'll explain it a little bit further then. So, if we go down to part E then, we have, if we learn a skill and then don't practice it, how well we can do it usually decreases over time. For example, if you learn to play the guitar and then don't play the guitar for a number of months, you'll probably not be as good at playing the guitar the first time you try it again. This effect can be modelled by the following equation, where A is equal to B times t plus 1 to the C, where A is a measure of how well the skill can be done at a certain time, B is a measure of how well the skill can be done t months later without practicing, and C is a constant, and A, B, C and T are real numbers. Part 1. Write C in terms of log 10A, log 10B, and log 10 of t plus 1. So what we want to be doing is we want to be taking all of these and putting them into log form. So we have log 10A is equal to the log of 10B, which is multiplied by t plus 1 to the C. Remember our rules of logs. We have log of 10A. This is going to be equal to the log of 10B plus the log of 10 t plus 1 to the C. We want to have this all in terms of C, so what I'm going to do is I'm going to take that log of 10b over to the other side. So here we have log 10 t plus 1 to the C, and equal that to the log of 10b subtracting log of 10a. Other way around, sorry. The log of 10a subtract the log of 10b. With logs, we can bring this power all the way around to the front. So what I'm going to have is C multiplied by the log of 10 t plus 1, equaling that to the right hand side again. And then divide both sides by the log of 10 t plus 1, so that it's all just in terms of C. So therefore C is going to be the log of 10a minus the log of 10b, and this whole thing gets divided by the log of 10t plus 1. Part 2. A student got 80% on a guitar exam. After 2 years of not playing the guitar, the student got 47% on the same exam. Use this to find the value of C in terms of the model. So, first of all, this model works in terms of months. So 2 years is the same as 24 months. Now we just plug everything back in. So we're looking for C, and that's going to be equal to the log of 10. When we let 80 go into the exam, or into the equation, we get that. We subtract away the log of 10, 47. And this whole thing gets divided by the log of 10. T is 24 months plus 1. So if you stick all of that into your calculator, what you're going to get is that this whole thing is equal to 0.165. And this is all correct to 3 decimal places. So any questions on that, just let me know. I'll get back to you as soon as I possibly can. So now we're going to be looking at the 2022 paper, question 6, paper 1 for the higher level maths exam. So it says, part A, the function f is defined as follows for x being an element of R. F is a mapping which sends x to the function x cubed minus 6x squared plus 3. Use calculus to find the coordinates of each of the following points. So 1 and 2 involve finding the local max and the local minimum point of f, and part 3 asks for the point of inflection of f. So let's just look at the first one, or parts 1 and 2. Whenever you're finding the local max mins or the point of inflection, what we're going to be doing is just solving a derivative of the function, whether it's the first or second derivative, equivalent to x, and whatever value we get, we stick it back into the original function, and then we're going to get y. So if we write this out again, we're going to have f of x is equal to x cubed minus 6x squared plus 3. So we find the derivative of this, f of x is going to be 3x squared minus 12x. That 3 is a constant, so we get rid of it. Or it just equals to 0, so we don't have to write in the second one. So We can simplify this by factorising out 3x from both terms, and then we're just left with x minus 4 in the middle. So we have 3x equaling 0, so x has to be equal to 0. And then we have x minus 4 is equal to 0, so then we just have x is equal to 4. As I said before, these 2 points we're just going to sub back into the original function, and they're going to give us the local max or the local min, and then we just have to figure out which is which. So if we find f of 0, that equals 3, so it gives us the point 0, 3. And then if we find f of 4, it gives us negative 29. So that's 4 minus 29. I'm not showing you doing these calculations because it's just sticking it into your calculator. So now we just need to figure out which one is which. Looking at this original function, what we have is positive x. So we know that it's going to have this sort of a shape, where that tails off and that tails off. So if we know that's going to be the fact and that it goes up, down, and then back up in some sort of way, and we plot this, we know that this point right here has to be 0, 3, and then this point right here, because it's further along, is 4 and negative 29. And in reality, our axes will go something like that. So we know that this first one is going to be the local max, and then the second one is the local min. And what I've done below is use GeoGebra just to graph this out. So if you type in that function, this is what it gives you. And we can see at the very top, although it's not written, this point right here is 3. So that gives us the point 0, 3, which is the max. And then if we go all the way down, we have this bottom point here, which is when x was equal to 4, which gave us negative 29. So we know the local minimum is going to be 4 minus 29, and the max is going to be 0, 3. Now we're going to be solving the point of inflection. How do we do that? Well, point of inflections are when it change from concave up to concave down. And how do we know, or how are we going to be able to find it? Well, where this would change from concave up to concave down is where we're going to change from this sort of a shape to this sort of a shape, as you can see here. The question doesn't ask which one's which, we just need to find the point in which it occurs. And how do we do that? Well, if we find the second derivative of the function and equal to 0, we're going to be able to solve it. So f double prime of x is equal to the derivative of f of x. So we're going to be looking back up and figuring out what this is. So 3x squared minus 12x, that's just going to go to 6x minus 12. Equal that to 0. And solve for x. We get x is equal to 2. Same as we did in the first step, we're just going to be finding f of 2 then. And if we figure out what that is, we're going to end up with the point minus 13, i.e. 2 minus 13. So the point of inflection is going to be 2 and minus 13. So if we look at the graph and we go to 2, down to minus 13, right here. So it's right on the graph. So we know it's going to be there. So it's at this point that if we just use a highlighter to distinguish the two, the function will go up and down. And at this point right here, if we change to yellow, it changes from going to down to up. You can think of it as kind of the midpoint between the two turning points, but to say it mathematically, it's the point where it goes from concave up to concave down. How do we know which one's which? Well, if we look at sort of the arms is what I'm going to call it. If we look at the left hand side red, this is pointing down and that's pointing down. And then if we look at the yellow one, this one's pointing up and so is one here. So the left hand side in this one, if you want to know, is equal to concave up. On the right hand side, concave down. Again, the question doesn't ask for this, but if you're wondering what one's which, or you get a similar question about which side of it is concave up and concave down, that's how you're going to be able to figure this out. So, going on to part B. The diagram below shows the graph of the cubic function g of x for some value of x between negative 2 and 2.5, where x is a real number. There's a local minimum point at minus 1 and 2, and a local maximum point at 1, 6. Write down the values, or the range of values of x for which g of x is increasing. If it's increasing, it means it's going upwards when we read it from left to right. So it also gives the minimum points. So we know this right here is a minimum, and then we know this right here is going to be a maximum point. So quick way of doing this, if we just divide it along the turning points, we can see that to the very left hand side, this is going down. In the middle, this is going up, and the right hand side, that's going down. So where does this occur? Between -1 and +1. So we know that x is strictly less than or greater than 1, but it's strictly greater than or equal to -1. Explain why the function does not have an inverse for a value of x between -2 and 2.5. We can get into injective and surjective functions of why they're in, and why we can find the inverse of that. We'll be getting into some further levels of algebra that you'd study at college, called algebraic structures, or sometimes an analysis of whatnot. But to explain this in an easy way, to be an injective function, or to find the inverse of a function, we can't have multiple values of x mapping to the same value of y, to put it simply in terms of this graph. So if we look at this graph, you can kind of use a straight line test. If at any stage we're able to move this straight line up and it contacts in more than one place, we can say that it's going to not be able to find the inverse of it. So if we look right here, we have the red line crossing at this point here, and all the way at this point here. So because it crossed at 3 separate points, it can't have an inverse. So we want to explain why. We can say that the y being equal to 3 has 3 x inputs. In other words, if we subbed in f of minus 1.5, this looks like it would be maybe minus 0.66, and then all the way over here we have call that 1.8. If we sub those 3 values into f of x, we'd get 3. So we have 3 values being mapped to by the same value of x. So that's why it can't